Today we're going to start with a quick review of assignment statements, which we've seen a couple times before, but I really want to hit home. Then we're going to move on to some quirky things that you have to deal with when you're doing arithmetic in Java. It's going to call back some stuff that you may have learned in a prior CS course, particularly about binary and how numbers are represented. As we said before, remember that the equal sign in Java is not the same mathematical equal sign that you're used to from math class. Instead, it's an assignment operator. It means, hey, whatever's on the right of this assignment operator is going to go into whatever's on the left. Oftentimes we think of it as gets. So in this case, the variable gets the expression. It gets the expression's value. We're assigning whatever's on the right to whatever's on the left. Here, in this code snippet, we declare a couple of variables, two doubles, we declare a string, we declare a scanner, and then we skip a bunch of stuff, a little ... waving our hands, and now we're assigning objects and values to those variables. So we're instantiating a new scanner object and assigning it to the reader variable. We're reading a value from the keyboard using the reader object and assigning whatever we get to the Fahrenheit variable. And then we're doing a bunch of calculations using the Fahrenheit variable and assigning whatever the result is to Celsius. Last one is just a regular assignment of a string literal to a string variable. Kwame Chen to the variable name. This is the stuff that can get a little interesting. Now, by and large, arithmetic expressions are not super complicated in Java. Most things work the same as regular math class as you're used to. Parentheses still do grouping and change the order of operations. You still have multiplication and division, then you have addition and subtraction. All of that is pretty good. One thing that's important to note is in algebra class, you might have been able to do x, y, and have that mean x times y. Of course, in Java, you can't do that. If you want to do a times b, you have to explicitly say a asterisk b. Here we've got a list of the operator precedences, essentially the order of operations in Java for some key operators. We won't spend too much time on this, but note how high up grouping and methods are. That's really important. That plus sign at precedence 3, that's not the plus sign you would use in addition. That's the unary plus. So that's how we specifically state that something is positive. That minus sign in precedence 3, that's not a subtraction sign, that's a unary minus sign. So that's how we indicate that something is negative. We'd put that in front of a number, -3. And you can see the rest of it is pretty straightforward. Assignment, as you see, is pretty low at the bottom. So all this stuff above assignment is going to happen before we actually do any assigning of any values to variables. So division is the first interesting thing that we come to when we're talking about arithmetic in Java. So the big challenge that we see is that things get a little different when we're working with integers versus floating point numbers. Okay, so if we have two floating point numbers, 5.0 divided by 2.0, well, that's pretty straightforward. That gives us 2.5. Now, 5 divided by 2, and let me be specific, that's integer 5 divided by integer 2, no decimals. That's going to give us an integer answer. So the way you can think about this, and we'll call this integer division, the way you can think about this integer division is we're saying, okay, integer 5 divided by integer 2 gives us 2 point something, and then we drop whatever fractional part there was in the answer, since 5 and 2 are both ints. Okay, so 5 divided by 2 actually just gives us integer 2. Now, we talked about what happens when it's a float divided by a float. We talked about an int divided by an int. Okay, now the question is what happens when we have mixed mode division. So a floating point number and an integer, a double and an int. Okay, as we said before, 5.0 divided by 2.0, 2.5. Fine, that's not mixed mode. 5 divided by 2, okay, fine. 5 divided by 2.0. So again, that's integer 5 divided by floating point 2.0 gives us 2.5. The reason for this is we say that the answer takes the double type because double is the larger, more inclusive of the two types. So the answer here gets the larger, more inclusive type. Note, it's not about the larger value because 5 is greater than 2.0. Really, it's about what's the larger type. Doubles are larger than ints. So you try a couple. I'm going to give you about 15 seconds. Take a look at these. Tell me what the number will be and what type it will be, whether it will be an int or a double, or an integer or a floating point number. So take a couple seconds and we will see what we get. Okay, go ahead and wrap up. If you need more time, just pause the video right now and take your time. Then unpause it when you're ready to go. I think these answers are pretty much in line with what we talked about before. An int divided by an int gives us an int. Double divided by an int is going to give us a double because the double is the more inclusive, larger type. 2 doubles give us a double answer, and 2 ints give us an int answer. It works that way with the other operations as well. Maybe you've seen the modulus operation before. Just as a quick review, this percent sign, we pronounce it as mod or modulus, and it essentially just means give us the remainder. So 9 mod 5 gives us 4 because 9 mod 5 is 1 remainder 4. 9.3 mod 5.1 gives us 4.2 because 9.3 divided by 5.1 is 1 with a remainder of 4.2. 9 mod 3 gives us 0. There's no remainder there. And 20 mod 3 gives us 2. Now you try a couple. Okay, hopefully you've got an answer by now. If not, just pause the video and start up again when you're ready to go. The answers are predictable here. 1, 3, and 0.1. Check yours to make sure you got the right thing. If you didn't, take another look. If you're doing modulus with one or both of the operands being negative, gets a little quirky. Here's the rule. You're going to calculate as if both were positive, and then you'll take the sign of whatever the left operand was. Okay, that's the convention. That's what people do. -8 mod -2, that's going to give us a negative answer. -8 mod +2 also gives us a negative answer. And 8 mod -2 gives us a positive answer. -4, -4, and 4. But, you know, this is a weird thing to do. This is a pretty nitty-gritty detail of the way modulus works. I can't remember the last time I've actually used modulus with negative numbers. Most people only use it with positive numbers because it's the remainder, and that's when it makes sense. Now, one tricky thing you can do is use modulus to check whether a number is even or odd. So if you mod a number by 2 and what you get back is 0, well, you know you have an even number. And if you mod a number by 2 and you get 1, you know you've got an odd number. 7 mod 2 is 1, 8 mod 2 is 0, 9 mod 2 is 1, 10 mod 2 is 0, 11 mod 2 is 1, 12 mod 2 is 0, and so on. That's a nice little trick. Now, I need you to step back to your prior computer science classes and remember how we represent data in a computer. We do it with bits. So we say that each one of these bits, each one of these zeros or ones is a bit, and we say that 8 of them strung together makes a byte. Now in Java, 4 bytes, which means 32 bits, makes an int, and 8 bytes makes a double. Let's take a closer look at what happens when we run up against the limits of an int, a 4-byte, 32-bit int in Java. Okay, so remember, 1 bit lets us represent 2 numbers, 0 and 1. 2 bits lets us represent 2 to the second numbers. Okay, that's 4 numbers. 3 bits lets us represent 8 numbers. That's 2 to the third power. So if we had 32 bits, which is what we have in Java with an int, that lets us represent 2 to the 32nd power numbers. Essentially, that's from 0 to just over 4 million, 4.3 million, basically. Now, that's a little misleading because actually we probably want to use both positive and negative numbers. So of those 32 bits, right, if we want to make half of them negative and half of them positive, we've sort of got to split them down the middle. And that's why what we do is make the largest bit in the whole number, that's the one that's all the way to the left, or as far left as we can go, that's the one that we make represent sign. So if that bit is 0, we know we're working with a positive number. If that bit is 1, we know we're working with a negative number. That means that the biggest int we can represent is 2,147,000. That means that the biggest int we can represent is 2,147,483,648, which, if you convert it to binary, looks like this. What if we were to try to add 1 to that and store a bigger number? Here's the rub. Java won't throw an error. It's just going to invert the sign and keep going. So you can see what happens. 0 and then 31 straight ones. If you add 1 to that, it becomes 1 and 31 straight zeros. Now, if you remember, that last bit all the way to the left in a 32-bit int, that's what we use to indicate sign. So that means that this number that was positive, when I added 1 to it, it became negative. Okay, that's weird. So here's what I did. I went ahead and wrote a little program. You can take a look at the code. This uses some structures that we haven't worked with yet, so don't feel pressured to look at it right now, but if you'd like to, you can. Essentially, what this does is it generates all the powers of 2 for up to the 40th power. It also converts each power of 2 into a binary string and prints out that binary string. So essentially, we're seeing both the human readable power of 2 and the representation of that power of 2 in the Java virtual machine. So you can see it here. We start with 2, and as you can see, that's, okay, a bunch of zeros, bunch of zeros, bunch of zeros, 0, 0, 0, 0, 0, 0, 1, 0. Okay, when we multiply that by 2 and we get the next power of 2, which is 4, that 1 shifts over one place. Multiplied by 2 again, the 1 shifts over again. Multiply by 2 again to get 16, the 1 shifts over again. You can follow this all the way through, come back here and wrap around at the top until we get here. Okay, well now we're at 0, 1, 0, 0, 0, 0, 0, 0, and so on. And the question is, what's going to happen the next time we shift the bit? Well, it turns out something really, really weird happens. We get a negative number. And it makes sense why, because if we just shift the bit one more time, as we've been doing every time we multiply by 2, we end up with 1, which means we have a negative number, and then a whole bunch of zeros. Now, my program kept going, and it kept multiplying by 2 again. So we multiplied this number, this huge negative number, and this binary string, we multiplied it by 2 again, and the next answer it gave us was 0. Now that's weird too, but it makes sense, because if you think, this bit really just got shifted one more time. But Java can only represent 32 bits in an int variable. So that bit, when it got shifted over one spot to the left, it really just sort of fell out of our variable. And that's why after this, if I were to keep running the program up to the 50th, 60th, 70th power, we would just still have 0 for all these values. So the behavior gets pretty unpredictable when you get to numbers that high with an int. We call this an arithmetic overflow error. Okay, there's no error message. Java didn't warn us about it, really. We just got a wrong answer. So this is something you got to watch out for when you think the numbers could get that high. Fortunately, you don't need to remember what those max values for ints are. It's built into Java, and you can get to it with integer.maxValue or integer.minValue, because the same thing happens if you try to subtract 1 from the smallest value that an int can hold, from the most negative value that an int can hold. Okay, you end up with a really, really positive number. Just things get really screwy when you're working at the extremes there. So if you're working with values that could get that big, you really want to check against integer.maxValue and integer.minValue. So think back to a couple minutes ago when we were working with mixed mode arithmetic. 3.14 times integer 3. Is that going to give us an int or a double? Hopefully you said double. 3.14 is a double. That's the larger, more inclusive type. So take a look at this example. We have a double D. We have an int I. I gets initialized to 45. And that makes sense. That's fine because we're taking an int literal and putting it into an int value. Good. D, that double, that gets the value of I. Okay, I is an int, and it's going into a double. That's fine too, because double is more inclusive than int. But if you do it the other way around, if you try to shove that double value, if you try to cram that double value into a much smaller int, you're going to have problems, and it's going to give you a syntax error. So we got to find a way around that, because maybe at some point we are going to have a double value, and we want to strip away the decimal part and stick it in an int. The way we do that is by casting, and it's essentially a way for us to convert one data type to another. So quick example here, coming back to what we were looking at a second ago. If you have an int I double D, okay, I equals the int version of 3.14. We're taking a double literal and cramming it into an int variable, but it's not going to throw an error at us because we're saying to Java, hey, you know what? I want you to turn this 3.14 into an int. So now the value of I after this assignment statement is going to be 3. Likewise, if I take this double variable D, okay, look, I've got 5 divided by 4. Now, something interesting happens here. Okay, I'm casting 5 and then dividing by 4 because casting has a higher precedence than division. That's unexpected, but it leads to some quirky things. if you take a look here, double, we have x and y. Okay, 5 divided by 4. Well, because double has a higher precedence than division, right, that 5 gets casted to a double before the division happens. So we end up with 5.0 divided by 4, which equals 1.25. Now, if we were to stick that 5/4 into parentheses, then we do the division. Integer 5 divided by integer 4 is going to be 1. Really, it's 1 point something, but we drop the decimal part. And then if we cast that integer to a double, we end up with 1.0 as the value of y. So, using parentheses, the order of casting makes a difference. You got to be real careful with precedence. One sort of tricksy use of casting is rounding numbers. So think about what happens with two test cases of this first statement. So suppose we assign some positive number. Let's say we assign 13.3 at first to x. Okay, well 13.3 plus 0.5 is going to give us 13.8. Okay, if we cast 13.8 to an int, well, that 0.8 just gets dropped off, and we end up with 13. Okay, so we took that 13.3 and we rounded it down appropriately to 13. But look, if we start with 13.7, all right, well, if x is 13.7 and I add 0.5 to it, so that means 13.7 plus 0.5 is 14.2, and I cast that 14.2 to an int, well, the 0.2 gets dropped, and now I have 14 as an int. So that 13.7 now got rounded up to 14. This is tricksy, and it works the other way too with negative numbers. So try it out for yourself. Come up with an example. Okay, there was a lot in this lecture, so you really want to take stock and make sure that you are solid on everything that we covered today. Big things you want to make sure you can handle: how you write assignment statements for variables. Make sure you can form mixed mode arithmetic that's between ints and doubles. Make sure you can do modulus. What happens if you add 1 to the maximum integer, or if you subtract 1 to the minimum integer? Okay, how do you actually get the value for the maximum and minimum integers in a Java program? And how can you cast to convert between an int and a double? What's the syntax look like? What happens to the values? And last of all, how can you cast in order to round an integer? Okay, so lots to handle from this lecture. Have a great day. See you next class.